Sometimes the most profound discoveries come not from building something bigger, faster, or more powerful, but from witnessing something that simply refuses to quit. Picture this like finding an ancient aqueduct that still delivers crystal-clear water after millennia. Chief Engineer Isabella Marchetti and her team at the Aeronautica Militare's Technical Depot 23 in Brindisi thought they understood aircraft engines until American Douglas C-47 Skytrains started rolling onto their tarmac with maintenance logbooks displaying an absolutely impossible figure: over 10,000 operational hours without major engine overhaul. What they were about to discover would shatter every assumption about aircraft engine design and reliability that Italian aviation had held for decades. The Mediterranean sun beat down mercilessly on the converted airfield at Brindisi in the summer of 1943. What had once been a bustling Regia Aeronautica fighter base, home to sleek Mach-E C-202 Folgores and powerful Savoia Marchetti bombers, now found itself transformed into Allied Technical Depot 23. The transition from Axis to Allied operations had been swift and jarring, leaving Italian aviation personnel scrambling to adapt to entirely new procedures, aircraft types, and maintenance philosophies. Isabella Marchetti stood at the edge of the tarmac, her engineer's eye taking in the organized chaos before her. At 34, she was one of the few women to hold a senior technical position in Italian aviation, having earned her credentials through sheer brilliance and an almost supernatural ability to diagnose engine problems that left her male colleagues baffled. Her dark hair was pulled back in a practical bun, and her coveralls bore the stains of a decade spent with her hands deep in aircraft engines. The irony wasn't lost on her that she, who had spent the war years keeping Italian fighters airborne against these very same Allied forces, was now responsible for maintaining their aircraft. But Isabella was a pragmatist above all else. The war had shifted, Italy needed to rebuild, and aircraft engines were aircraft engines, regardless of which flag flew above the hangar. Her team reflected the strange new reality of post-armistice Italy. Deputy Chief Engineer Marco Sant'Angelo, a gruff veteran who had cut his teeth on Fiat radial engines in the 1930s, now found himself puzzling over American engineering drawings. Senior mechanic Elena Rossi, one of the handful of women who had been allowed into technical roles during the desperate final years of the war, brought a meticulous attention to detail that had saved countless Italian pilots' lives. And then there was young Tommaso Benedetti, barely 22, whose mathematical mind and fresh engineering degree from the University of Bologna made him invaluable for understanding the increasingly complex systems they encountered. The depot buzzed with activity as American Lend-Lease aircraft arrived in steady streams. P-38 Lightnings, destined for Italian co-belligerent Air Force squadrons, shared hangar space with B-25 Mitchells being prepared for supply runs to Yugoslavia. But it was the steady flow of C-47 Skytrains that would soon capture Isabella's complete attention and challenge everything she thought she knew about aircraft engine design and reliability. The morning of August 15, 1943, the Feast of the Assumption, ironically enough, brought the arrival of 12 Douglas C-47 Skytrains from the 315th Troop Carrier Squadron. These weren't pristine aircraft fresh from the Douglas factory in Long Beach. These were battle-worn veterans, their olive-drab paint faded and chipped, their aluminum skin bearing the scars of flak fragments and the wear patterns of countless cargo loadings. Isabella assigned herself to personally inspect the lead aircraft, serial number 4292847, which bore the nose art Sicilian Express along with an impressive tally of mission markers. As she climbed into the cockpit to review the maintenance logs, she experienced what she would later describe as the most profound moment of professional shock in her career. The Form 1A maintenance record, meticulously maintained in the precise handwriting of various American flight engineers, told an impossible story. The port engine, a Pratt & Whitney R1830-92 Twin Wasp, serial number 4185639, showed 10,847 total operational hours. The starboard engine had accumulated an even more staggering 11,203 hours. Both engines were listed as original installation, no major overhaul required. Her hands actually trembled as she flipped through page after page of routine maintenance entries. Oil changes every 50 hours, spark plug replacements at 100-hour intervals, minor component changes here and there, but nowhere, absolutely nowhere, was there any record of the massive teardowns, ring replacements, bearing changes, and cylinder overhauls that Italian aviation considered inevitable every 400 to 500 hours of operation. She called for Elena Rossi, her most trusted mechanic. "Elena, come up here and tell me I'm reading these numbers wrong." Elena, a compact woman with premature gray hair and hands that could diagnose engine problems through touch alone, climbed into the cockpit and studied the logbooks. Her weather-beaten face went through a series of expressions: confusion, disbelief, and finally a kind of awed respect.
"Madonna mia," she whispered, using her fingers to trace the hour totals. "Isabella, these numbers, if they're accurate, these engines have been running for almost 6 years straight. Our Piaggio P12 engines would be scrap metal after 800 hours." To understand the magnitude of what Isabella and her team were witnessing, one must appreciate the fundamental philosophical differences between Italian and American approaches to aircraft engine design in the 1940s. Italian aviation had always prided itself on elegance and efficiency. Their engines were marvels of precision engineering, lightweight, sophisticated, and pushed to the absolute limits of their design parameters. The Piaggio P12 engines that powered the Savoia Marchetti SM-82 transports were works of art. Complex variable pitch propeller mechanisms, intricate cooling systems, and metallurgy that squeezed every possible horsepower from every pound of weight. But this pursuit of perfection came at a cost. Italian engines were temperamental creatures that demanded constant attention. Pilots learned to baby their power plants, mechanics became artists of adjustment and fine-tuning, and maintenance schedules were aggressive affairs that assumed regular major overhauls were simply the price of aviation. Marco Santangelo, with his 30 years of Italian aviation experience, summed up the prevailing attitude perfectly. "Our engines are like prima donnas at La Scala, magnificent when they perform, but they require constant care and attention to maintain their brilliance." The American R1830 Twin Wasp, by contrast, represented a completely different philosophy. Where Italian engines were racehorses, the Twin Wasp was a draft horse. It was heavier than its Italian counterparts, seemingly overbuilt for its power output, and designed with what appeared to be almost wasteful safety margins. American engineers had approached the problem from an entirely different angle. Instead of pushing materials and design to their theoretical limits, they had built engines that operated well below their maximum stress levels. Components were sized not for minimum weight, but for maximum durability. Cooling systems were designed not for elegance, but for reliability under the worst possible conditions. Tommaso Benedetti, with his fresh engineering perspective, was the first to articulate what they were really seeing. "It's not that the Americans can't build sophisticated engines," he observed during one of their evening analysis sessions. "It's that they chose not to. They've prioritized reliability over every other consideration." This revelation was simultaneously humbling and fascinating for the Italian team. They had spent decades perfecting the art of extracting maximum performance from minimum weight, only to discover that there was an entirely different approach that prioritized longevity over peak performance. Isabella Marchetti was not a woman to accept mysteries without investigation. By the third week of August 1943, she had organized her team into what she privately called Operation Longevità, a systematic investigation into the secrets of American engine reliability. The investigation began with a complete teardown of R-1830 engine serial number 4173492, which had accumulated 9,634 hours and was scheduled for routine inspection. What they found inside challenged every assumption they held about internal combustion engines. Elena Rossi, performing the cylinder inspection, called out measurements that seemed impossible. Cylinder bore wear, 0.003 inches maximum variation, piston ring gaps still within new engine specifications, bearing clearances, she paused, rechecking her measurements, bearing clearances are actually tighter than some of our Italian engines after 200 hours. The connecting rods showed no signs of stress cracking. The crankshaft journals were smooth and true. The valve guides, which Italian mechanics expected to replace every 600 to 800 hours, appeared virtually unworn. Most shocking of all, the cylinder heads showed none of the warping and cracking that plagued Italian engines operating in the Mediterranean heat. Marco Santangelo, his weathered hands running over the pristine internal components, shook his head in amazement. In 30 years of aviation, I've never seen an interior engine this clean after 9,000+ hours. Our P-12 engines look like they've been through a war zone after 500 hours. The materials analysis proved equally surprising. Tommaso had arranged for metallurgy testing at the University of Body's engineering department. The results showed standard aluminum alloys and conventional steel compositions, nothing revolutionary or exotic. The Americans hadn't achieved longevity through superior materials, but through superior design philosophy. One of the most significant discoveries came when the team focused on the engine cooling systems. Italian engines, in their quest for weight savings, utilized minimal cooling capacity with precise temperature control. This worked beautifully under ideal conditions, but left little margin for error when operating in hot climates or under high stress. The American Twin Wasps cooling system was almost absurdly robust by Italian standards. Massive cylinder cooling fins provided heat dissipation capacity that seemed excessive for the engine's power output. The oil cooling system included provisions for extreme operating conditions that Italian engines would never be expected to encounter. Elena Rossi made the key observation during a particularly hot afternoon inspection. Look at this oil temperature gauge reading, 185 degrees Fahrenheit after 2 hours of ground running in 95 degrees weather. Our P-12 engines would be running 220 to 230 degrees under the same conditions.
British meticulousness in mechanical construction had led to a crucial realization. Italian engines operated much closer to their thermal limits, which accelerated wear on all internal components. The American approach of massive overcooling meant that engine components operated in a much more benign thermal environment, dramatically extending their service life. Isabella began to see the larger pattern. They've designed these engines to operate as if they're constantly under emergency conditions, she noted in her growing stack of investigation reports. What we consider normal operating parameters, they treat as stress conditions. The investigation into lubrication systems proved equally revealing. Italian aircraft engines utilized sophisticated oil circulation systems with precise pressure controls and minimal oil capacity, another weight-saving measure that worked well under ideal conditions. The R-1830's oil system was almost comically over-engineered by Italian standards. Oil capacity was nearly double what Italian engineers would consider necessary. The oil pump was sized for flow rates that seemed excessive. The filtration system included multiple stages and bypass provisions that Italian designs would consider redundant. But the real revelation came when they analyzed the oil change intervals and procedures. Italian maintenance schedules called for oil changes every 25 to 30 hours, with oil analysis and careful monitoring of contamination levels. The American procedures called for 50-hour oil changes with much less sophisticated monitoring. How can they run twice as long between oil changes and still maintain better engine condition? Elena wondered aloud during one of their evening analysis sessions. The answer they discovered lay in the massive overcapacity of the American system. Where Italian engines operated with precisely calculated oil quantities, the Twin Wasp's generous oil capacity meant that contamination was diluted to much lower concentrations. The oversized oil coolers meant that thermal breakdown occurred much more slowly. The robust filtration system removed contaminants that would accumulate in Italian engines. Perhaps the most profound difference was discovered when Isabella's team studied the American maintenance procedures and compared them to Italian practices. Italian maintenance was an art form, skilled mechanics who could diagnose problems through engine sound, who adjusted carburetor mixtures by feel, who could detect bearing problems through subtle vibration changes. American maintenance procedures were completely different. They were standardized, methodical, and designed to be performed by mechanics with far less specialized training. Where Italian procedures relied on the expertise and intuition of master mechanics, American procedures were engineered to be foolproof. Tommaso Benedetti spent days translating and analyzing the technical orders that governed Twin Wasp maintenance. What he found was simultaneously insulting and brilliant. These procedures are written as if the mechanics are idiots, he observed. Everything is specified down to the exact torque values, the precise adjustment procedures, even the order in which inspections should be performed. But this apparent dumbing down had profound benefits. It eliminated the variability that came with relying on individual mechanic expertise. It ensured consistent maintenance quality regardless of who performed the work. Most importantly, it prevented the kind of well-intentioned improvements that Italian mechanics often made to standard procedures. Elena Rossi, initially offended by the implication that American mechanics needed such detailed guidance, gradually came to appreciate the wisdom of the approach. "Our best mechanics are artists," she admitted, "but our average mechanics make mistakes that these procedures would prevent." The investigation took an unexpected turn when Isabella discovered the extent of American documentation and record-keeping. Italian aircraft maintenance relied heavily on the memory and experience of individual mechanics. Records were kept, but they were often brief and assumed significant background knowledge on the part of anyone reading them. American maintenance records were exhaustively detailed. Every component change, every adjustment, every inspection was documented with serial numbers, part numbers, and cross-references to technical manuals. The C-47s they were inspecting carried complete maintenance histories that told the story of every significant event in each aircraft's operational life. More importantly, this documentation system allowed for trend analysis and predictive maintenance. American engineers could analyze failure patterns across entire fleets, identify components that required design improvements, and develop maintenance procedures based on actual operational data rather than theoretical calculations. "Look at this," Isabella said, spreading out months of maintenance records on her desk. "They've tracked the performance of every major component across hundreds of aircraft. They know exactly how long spark plugs last in different climates, which bearings fail first under various operating conditions, even how propeller blade wear patterns change with different cargo loads." This systematic approach to data collection and analysis represented a fundamentally different way of thinking about aircraft maintenance. Where Italian aviation relied on the accumulated wisdom of experienced mechanics, American aviation was building a scientific database of component performance and failure modes.
3 weeks into Operation Longevità, Isabella experienced what she would later describe as her first American moment, a flash of understanding that began to illuminate the broader philosophy behind Twin Wasp reliability. She was reviewing the technical specifications for cylinder head temperatures when she noticed something that had initially seemed like a design flaw. The Twin Wasp cylinders were designed to operate at temperatures that Italian engineers would consider dangerously low, temperatures that would indicate incomplete combustion or insufficient power extraction. But as she studied the data more carefully, Isabella realized this wasn't a flaw. It was the key insight. American engineers had deliberately designed the engine to operate at temperatures well below the theoretical optimum. They'd sacrificed a small amount of power output in exchange for dramatically reduced thermal stress on all engine components. "They're not trying to extract every possible horsepower," she explained to her team during one of their evening sessions. "They're designing engines that will run forever at 80% of their theoretical maximum rather than engines that produce maximum power for 400 hours before requiring overhaul." This revelation began to unlock the broader American approach, where Italian engineering pushed every component to its design limit. American engineering built in massive safety margins. Where Italian designers optimized for peak performance, American designers optimized for sustained reliability. Not everyone on Isabella's team embraced these discoveries with equal enthusiasm. Marco Santangelo, in particular, struggled with what he saw as a fundamental betrayal of engineering excellence. "These Americans have no artistry," he complained during one particularly heated discussion. "They build engines like plumbers build pipes, functional, crude, without elegance. Where's the beauty in an engine that any fool can maintain?" This resistance wasn't merely about professional pride. Italian aviation culture had always celebrated the symbiotic relationship between machine and operator. Italian pilots were expected to understand their engines intimately, to nurse them through difficult conditions, to coax maximum performance through skill and intuition. Italian mechanics were craftsmen who took pride in their ability to extract reliable service from temperamental machines. The American approach seemed to eliminate this human element. Their engines didn't require artistry to maintain, they simply required adherence to procedures. Their pilots didn't need to understand the subtle moods of their power plants, they simply followed standardized operating procedures. "But Marco," Elena Rossi pointed out, "look at the results. These American engines just keep running. Our beautiful, artistic Italian engines are grounded for maintenance, while these crude American workhorses are still flying missions." As the investigation progressed through September 1943, Isabella began to see implications that extended far beyond aircraft engines. The American approach represented a fundamentally different philosophy of engineering and manufacturing that could revolutionize Italian industry. The standardization that seemed crude to Italian eyes actually enabled mass production on a scale that Italy had never achieved. The simplified maintenance procedures that insulted Italian mechanics actually allowed for rapid training of personnel and consistent maintenance quality across vast geographic distances. Most importantly, the American design philosophy prioritized reliability over performance in ways that could transform military aviation. An engine that flew 10,000 hours before requiring overhaul meant that aircraft could be deployed to remote locations without extensive maintenance infrastructure. It meant that training programs could focus on operations rather than constant maintenance. It meant that military planners could count on aircraft availability in ways that Italian aviation had never experienced. Tommaso Benedetti, with his mathematical mind, began calculating the broader implications. If we assume a 500-hour mean time between overhaul for Italian engines versus 10,000 hours for American engines, the Americans need 95% fewer maintenance facilities to support the same operational tempo. They can deploy aircraft to locations where we would require full engine shops. Despite their growing understanding of American design philosophy, significant mysteries remained. The most puzzling was the question of manufacturing quality. Italian engines were hand-built by skilled craftsmen, with individual components carefully fitted and adjusted. How could mass-produced American engines, built in enormous factories by semi-skilled workers, achieve such remarkable reliability? This question led Isabella to focus on manufacturing tolerances and quality control procedures. What she discovered challenged another fundamental assumption about precision engineering. American manufacturing specifications called for much looser tolerances than Italian practice, where Italian engines were built to tolerances measured in thousandths of an inch. American specifications allowed for much greater variation. This seemed to contradict everything Isabella knew about precision engineering. But as she studied the data more carefully, she realized that the Americans had taken a systems approach to tolerance management. Individual components might be less precisely manufactured, but the overall engine design accommodated this variation through generous clearances and robust materials. They've designed engines that work well with imperfect components, she noted in her investigation journal. We design engines that require perfect components to work at all.
British. By early October 1943, Isabella's team had accumulated dozens of measurements, filled notebooks with observations, and developed theories about everything from materials science to manufacturing philosophy. But they were still missing the crucial insight that would tie all their discoveries together. The breakthrough would come from an unexpected source. Master Sergeant Patricia "Pat" Williams of the 64th Troop Carrier Squadron had been flying and maintaining C-47's since 1940. She had nursed these aircraft through the steaming jungles of Burma, the freezing altitudes of the Himalayas, and the scorching deserts of North Africa. More importantly, she had been part of the original engineering team at Pratt & Whitney that had developed the maintenance procedures Isabella's team was struggling to understand. Sergeant Williams had arrived at Depot 2-3 on October 12th, originally scheduled for just a brief technical consultation, but when she heard about the Italian investigation into twin wasp longevity, she requested permission to spend additional time with Isabella's team. "Ma'am," she said to Isabella during their first meeting, "I understand you're trying to figure out how our engines run so long. I think I can save you some time and effort because what you're looking for isn't in the engines themselves, it's in how we think about the problem of reliability." What Sergeant Williams was about to reveal would not only solve the mystery of the 10,000-hour engine life, but would fundamentally change how Isabella Marchetti approached engineering problems for the rest of her career. The American secret wasn't in superior materials, advanced manufacturing, or revolutionary design. It was something much more profound and much more transferable to other engineering challenges. But that revelation would have to wait until the autumn rains began to fall on the Brindisi airfield, when Pat Williams would sit down with Isabella's team and explain a concept that American industry had been developing since the early days of mass production, a concept that would eventually transform manufacturing worldwide. Sometimes the greatest engineering breakthroughs come not from pushing the limits of what's possible, but from understanding the difference between what's theoretically optimal and what actually works in the real world. The morning mist hung low over Brindisi airfield as Master Sergeant Patricia "Pat" Williams stepped off the C-47 that had brought her from the 64th Troop Carrier Squadron's base in Sicily. At 38, she was a rarity in military aviation, a woman who had not only earned her stripes as a flight engineer, but had also been part of the original design team at Pratt & Whitney's East Hartford facility, where the R-1830 Twin Wasp had been born. Isabella Marchetti watched from the hangar doorway as Pat approached, her confident stride and the weathered leather flight jacket telling the story of thousands of hours in the air. Pat's auburn hair was pulled back in regulation fashion, but her eyes held the kind of deep knowledge that only comes from years of intimate familiarity with complex machinery. "Chief Engineer Marchetti," Pat extended a calloused hand, "I understand you and your team have been trying to solve the mystery of our engine longevity. Mind if I save you some time and effort?" Isabella had expected another routine technical consultation, perhaps some clarification of maintenance procedures or parts specifications, but what she got instead was about to revolutionize her understanding of not just aircraft engines, but the entire philosophy of reliable engineering design. That evening, as the Mediterranean sun set behind the hangars of Brindisi airfield, Master Sergeant Patricia "Pat" Williams sat down with Isabella's team around a collection of engine components they had been analyzing for weeks. In her hands, she carried a worn leather portfolio that would prove to contain the keys to understanding American industrial philosophy. "Before I explain anything," Pat began, "I need to ask you a question. When you designed an engine, what's your primary goal?" Marco Santangelo answered immediately, "Maximum power to weight ratio, obviously. Every horsepower matters, every pound counts." Eleanor Rossi nodded agreement. "Efficiency and performance. We push every component to its design limit." Young Tommaso Benedetti added, "Elegance of design, the perfect balance of all systems working at their theoretical optimum." Pat smiled knowingly, "And that's exactly why your engines need overhauls every 400 hours, while ours run for 10,000. You're solving the wrong problem." She opened her portfolio and spread out a collection of documents that Isabella would later describe as the most important engineering papers she had ever seen. These weren't just technical specifications, they were the philosophical foundations of American industrial design. In 1923, a man named Walter Schuhart at Western Electric developed something called statistical process control. Most people think it's about manufacturing quality, but it's really about understanding variation and designing systems that work despite imperfection.
Pat Williams began to unveil a concept that was completely foreign to Italian engineering tradition. The idea that reliability should be designed into a system from the beginning, rather than achieved through precision manufacturing and skilled operation. "Your Italian engines are like Formula One race cars," she explained, using an analogy that resonated with the team. "Absolutely brilliant when everything is perfect. Perfect fuel, perfect operating conditions, perfect maintenance, perfect piloting. But the moment any variable falls outside optimal parameters, performance degrades rapidly." She pulled out a graph showing engine reliability curves. "Our twin Wasps are designed like farm tractors. They're built to operate reliably under the worst possible conditions with the least skilled operators and minimal maintenance infrastructure." Isabella studied the reliability curves with growing fascination. The American approach showed a shallow, extended degradation pattern, while Italian engines displayed steep performance cliffs once optimal conditions were exceeded. "But how do you achieve this without sacrificing performance entirely?" Isabella asked. Pat's answer would reshape Isabella's entire career. By understanding the difference between theoretical maximum performance and sustained operational capability, we deliberately operate our engines at 70–80% of their theoretical maximum, which gives us enormous margins for variation, wear, and imperfect conditions. Tommaso Benedetti, with his mathematical mind, immediately grasped the implications. "You're trading peak performance for area under the curve, total operational capability over time, rather than maximum instantaneous output." "Exactly," Pat confirmed. "An engine that produces 1,200 horsepower for 400 hours gives you 480,000 total horsepower hours. An engine that produces 1,000 horsepower for 10,000 hours gives you 10 million horsepower hours. Which one is actually more powerful?" The next revelation came when Pat explained how American manufacturing philosophy supported this reliability-first approach. She produced a series of photographs from Pratt & Whitney's East Hartford facility that showed an entirely different approach to engine production. "Your Italian engines are hand-built by master craftsmen," she observed. "Each one is slightly different. Each one reflects the particular skills and techniques of its builder. It's beautiful, but it's also unreliable at scale." The photographs showed vast factory floors where hundreds of workers, many of them women, assembled engines using standardized procedures and fixtures. Every component was manufactured to specifications that allowed for significant variation while still ensuring proper function. We've learned that consistency is more important than precision, Pat explained. A component that's consistently good enough is more reliable than a component that's sometimes perfect and sometimes flawed. Eleno Rossi struggled with this concept. But surely precision manufacturing produces better engines. Pat's response challenged everything the Italian team believed about quality. Precision manufacturing produces engines that require precision maintenance, precision fuel, precision operating procedures. We build engines that work well with imprecise everything else. She showed them tolerance specifications that seemed shockingly loose by Italian standards. Where Italian engines required components machined to thousandths of an inch, American specifications allowed variations that Italian engineers would consider sloppy workmanship. But here's the key, Pat continued. We designed the entire system to accommodate that variation. Instead of trying to eliminate variation, which is impossible at scale, we designed systems that function reliably despite variation. Marco Santangelo examined the specifications with growing amazement. You've essentially designed engines that are impossible to assemble incorrectly. That's exactly right. We've eliminated as many opportunities for human error as possible, both in manufacturing and in field maintenance. The most profound revelations came when Pat explained American maintenance philosophy. She pulled out a complete set of technical orders for the R-1830, documents that Isabella's team had been studying for weeks without fully understanding their deeper implications. Your maintenance procedures assume that every mechanic is an artist who understands engines intuitively, Pat observed. Our procedures assume that most mechanics are competent technicians who follow instructions precisely. She demonstrated by walking through a routine inspection procedure. Where Italian maintenance relied on a mechanic's ability to hear subtle changes in engine sound or feel variations in vibration, American procedures specified exact measurement techniques, precise criteria, and standardized corrective actions. We've systematized expertise. Instead of requiring every mechanic to develop intuitive understanding over decades, we've captured that expertise in procedures that can be learned in months. Elena Rossi initially bristled at this approach. But what about the artistry, the relationship between mechanic and machine? Pat's response was both pragmatic and profound. Artistry is beautiful, but it doesn't scale. When you need to maintain thousands of aircraft across dozens of countries with mechanics who speak different languages and have different levels of training, artistry becomes a liability.
She showed them failure analysis reports that demonstrated how American systematic maintenance had identified and eliminated failure modes that Italian intuitive maintenance had never recognized. By collecting data across entire fleets, American engineers could spot patterns that individual mechanics would never see. Your best mechanics are probably better than our average mechanics, Pat admitted, but our worst mechanics are much better than your worst mechanics, and in war, that's what matters. Perhaps the most revolutionary concept Pat introduced was what she called systems thinking, the idea that engine reliability was determined not just by individual component quality, but by how all components interacted under real-world conditions. You design engines by optimizing each component individually, Pat observed. We design engines by optimizing the interactions between components. She used the cooling system as an example. Italian engines used precisely calculated cooling capacity that worked perfectly under ideal conditions. American engines used massive overcooling that maintained safe temperatures under the worst possible conditions. Your approach assumes perfect conditions, Pat explained. Our approach assumes imperfect conditions and designs for worst-case scenarios. Isabella began to see the broader pattern. You're not just building engines differently, you're thinking about the entire operational environment differently. Pat nodded enthusiastically. Exactly. We design for the real world, not the theoretical world.
Real pilots make mistakes. Real mechanics work in poor lighting with inadequate tools. Real weather creates conditions that aren't in the textbooks. Real fuel isn't perfectly refined. Real operating conditions include dust, moisture, temperature extremes, and maintenance delays. This systems approach extended to every aspect of engine design. Where Italian engineers optimized for performance under ideal conditions, American engineers optimized for acceptable performance under all conditions. Tommaso Benedetti was furiously taking notes. This is essentially a statistical approach to engineering design. You're designing for the distribution of real-world conditions rather than the ideal case. That's a very sophisticated way to put it, Pat agreed. We design engines that work well across the entire range of likely operating conditions rather than engines that work perfectly under narrow, optimal conditions. Not everyone on Isabella's team embraced these revelations immediately. Marco Santangelo, in particular, struggled with what he saw as a fundamental compromise of engineering excellence. This is engineering for mediocrity. You're deliberately making engines worse than they could be. Pat's response would become legendary among the Italian engineers who witnessed it. Marco, let me ask you something. Would you rather fly in a beautiful aircraft that crashes or an ugly aircraft that gets you home safely? She pulled out operational statistics that told a devastating story. Italian aircraft had achieved remarkable performance when everything worked perfectly, but their operational readiness rates were abysmal. American aircraft achieved lower peak performance but maintained much higher availability rates. Your fighters might be faster in perfect conditions, but our bombers actually complete their missions. Your engines might produce more horsepower per pound, but our engines are actually running when we need them. This led to the most heated discussion of the entire investigation. Isabella found herself mediating between two fundamentally different philosophies of engineering excellence. Elena Rossi finally articulated what everyone was feeling. Are we wrong to value artistry and precision? Are we wrong to push for maximum performance? Pat's answer revealed the deeper wisdom of American industrial philosophy. You're not wrong to value those things, but you need to understand when to prioritize them and when to prioritize other values. In racing, precision and peak performance matter most. In war, reliability and availability matter most. The key is designing for your actual requirements, not your theoretical ideals. The breakthrough came when Pat challenged Isabella's team to redesign a maintenance procedure using American principles. She selected a routine carburetor adjustment that Italian mechanics performed by ear and feel, a procedure that required significant skill and experience. Show me how you would redesign this procedure so that a newly trained mechanic could perform it correctly every time, Pat challenged. Working together, the team developed a step-by-step procedure that used specific measurement tools, documented settings, and verification steps. Instead of relying on a mechanic's ability to hear subtle changes in engine sound, they created a procedure that used manifold pressure readings and tachometer indications. The result was revelation. The new procedure not only eliminated the variability associated with different mechanic skill levels, but it also achieved more consistent carburetor settings than even the most experienced mechanics had been achieving through intuitive methods.
You've just experienced the American approach, Pat explained. We systematize expertise so that good results don't depend on exceptional people. Isabella was amazed by the implications. This could revolutionize not just aircraft maintenance, but industrial processes throughout Italy. That's exactly what happened in America, Pat confirmed. This philosophy transformed our entire manufacturing economy in the 1920s and 1930s. It's how we were able to ramp up production so quickly when the war started. Pat's final major revelation concerned the American approach to data collection and analysis. She produced charts and graphs that tracked engine performance across the entire American aviation fleet, data that revealed patterns invisible to individual mechanics or even individual bases. Every engine failure teaches us something, Pat explained. We collect data on every component failure, every maintenance action, every operational parameter. This allows us to continuously improve our designs and procedures. The scope of American data collection was staggering.
They tracked spark plug life by climate zone, oil consumption patterns by operating altitude, bearing wear rates by fuel quality, and hundreds of other variables that built a comprehensive picture of engine behavior in service. This is why our engines keep getting more reliable, Pat continued. We're not just building engines, we're building a knowledge system that makes each generation better than the last. Isabella realized that this data-driven approach could transform Italian aviation. Instead of relying on the accumulated wisdom of individual mechanics, they could build a systematic understanding of aircraft reliability that improved continuously. Tommaso Benedetti was particularly excited by this aspect. This is essentially turning engineering into a science rather than an art. You're applying scientific method to industrial design. Exactly, Pat agreed, and the results speak for themselves. Our 1943 engines are dramatically more reliable than our 1933 engines, not because we've discovered new materials or revolutionary designs, but because we've systematically eliminated failure modes through data analysis. By November 1943, Isabella's team had completely transformed their approach to aircraft maintenance. They had implemented American-style procedures throughout Depot 23, achieving remarkable improvements in aircraft availability and maintenance efficiency. More importantly, they had internalized the philosophical lessons Pat Williams had taught them. Instead of pursuing theoretical perfection, they focused on practical reliability. Instead of depending on individual expertise, they systematized knowledge. Instead of optimizing individual components, they optimized entire systems. The results were dramatic. Aircraft that had previously required extensive maintenance to achieve brief periods of availability now operated reliably for extended periods with routine maintenance. Mechanics who had previously struggled with complex procedures now achieved consistent results using standardized methods. Elena Rossi, who had initially resisted the American approach, became one of its most enthusiastic advocates. "I understand now," she told Isabella. "We were solving the wrong problem. We were trying to make perfect engines instead of trying to make reliably good engines." Marco Santangelo took longer to embrace the new philosophy, but even he eventually acknowledged its effectiveness. "It's not as elegant as our traditional approach, but I have to respect results. These American engines just keep running." The transformation at Depot 23 didn't go unnoticed. By early 1944, Italian aviation authorities were implementing American-inspired maintenance procedures throughout their organization. The reliability improvements were so dramatic that other European air forces began requesting technical exchanges to learn American methods. Isabella Marchetti became a leading advocate for what she called reliability engineering, the systematic application of American industrial philosophy to Italian design challenges. After the war, she would help rebuild Italian aviation industry using principles learned from Pat Williams and the Twin Wasp investigation. The broader implications extended far beyond aviation. Italian manufacturing industry began adopting American approaches to quality control, systematic procedures, and data-driven improvement. The post-war Italian economic miracle owed much to the industrial philosophy lessons learned from American aviation engines. Years later, Isabella would reflect on the profound lessons learned during those intense months in 1943. The Americans' achievement wasn't in building better engines, it was in understanding what better really meant in practical terms. The Americans taught us that engineering excellence isn't about pushing the theoretical limits of performance, it's about consistently delivering the performance that's actually needed under real-world conditions. The Twin Wasp's 10,000-hour service life wasn't the result of superior materials, revolutionary design, or exceptional manufacturing. It was the result of a philosophical approach that prioritized sustained reliability over peak performance, systematic procedures over individual artistry, and data-driven improvement over traditional wisdom.
Pat Williams had returned to her squadron in December 1943, but her influence on Italian aviation would last for decades. The procedures she had helped Isabella's team develop became standard throughout Italian aviation. The reliability philosophy she had taught became foundational to Italian post-war industrial development.
The C-47s that had first shocked Isabella's team with their impossible hour counts continued flying well into the post-war era. Many accumulated over 20,000 hours of service life, numbers that would have seemed like fantasy to the Italian engineers who first encountered them in 1943. But the real legacy wasn't in the engines themselves. It was in the transformation of thinking that occurred when Italian precision engineering met American reliability philosophy. The synthesis of these approaches would eventually influence engineering education, industrial design, and manufacturing processes throughout Europe. Isabella Marchetti went on to become one of Italy's leading industrial engineers, helping to design the systematic approaches that fueled Italy's post-war economic growth. Eleanor Rossi established training programs that taught American-style, systematic maintenance procedures to a generation of Italian technicians. Even Marco Santangelo eventually embraced the new philosophy, becoming an advocate for reliability-focused design in Italian aerospace industry. The mystery of the 10,000-hour engine life had been solved, but the solution had revealed something far more valuable than aircraft engine design secrets. It had revealed a completely different way of thinking about engineering problems, a way of thinking that prioritized what actually worked over what theoretically should work. In the end, the greatest discovery wasn't about engines at all. It was about the power of designing systems that work reliably in an imperfect world, operated by imperfect people, under imperfect conditions. That lesson would prove far more valuable than any individual technical achievement, influencing not just aviation, but the entire approach to modern industrial design. The American Twin Wasp engines had indeed run for 10,000 hours without major overhaul. But more importantly, they had taught an entirely different philosophy of engineering that would reshape how the world thought about reliability, quality, and the true meaning of technological excellence. The greatest engineering achievement isn't building the most sophisticated machine. It's building the machine that works reliably when everything else goes wrong.